All right, we're going to go through the graph analysis review. So this is basically what we could use whenever we're looking at a graph or given an equation and asking about extrema. So the first thing is our first derivative. That is always where your derivative is equal to 0 or does not exist. It helps us find our critical points. And the places where it is equal to 0, you would find your derivative first and then find the values for x that set it equal to 0. Our does not exist is if we have a rational function, we would set our denominator equal to 0. It's also wherever we have those corners, cusps, or vertical tangents. And when you see that f prime is positive, it means that the function f is increasing. That would be, for example, if we had some interval, if we're given a graph and we see that it's negative, positive, negative, we would say that f prime is, or that f is increasing from a to b. And a lot of times when they talk about increasing and decreasing intervals, they will often on the AP exam use brackets or say that it's increasing from A to B. We always use parentheses because if these are our critical points, we know our derivative is 0. So we wouldn't necessarily say it's increasing at that point, but for some reason on multiple choice problems on the free response, increasing and decreasing, they often use brackets. We would say where our derivative is negative would be where f is decreasing, and whenever we're looking at graphs, increasing is always above the x-axis and decreasing is where our derivative graph would be below the x-axis. So that's when we're looking at our derivative graph. So if we saw something like this, we would say it's decreasing from A to B. And like I said, they'll oftentimes use brackets for that. A point of inflection is where our concavity changes. Now our potential points of inflection are kind of like our critical points for the second derivative. It's where f double prime of x equals 0, or where f double prime of x does not exist. But the other thing that has to happen is in order to be a point of inflection, f double prime of x must change signs. So it has to go from positive to negative or negative to positive. So in order to be a point of inflection, it must have both of these things, where the second derivative is 0 or does not exist, and the second derivative changes signs. Where our second derivative is positive is where it's concave up, looks like this, and if you're looking at an f prime graph, it would be where the f prime graph increases or has a positive slope. Where the second derivative is negative, it would be concave down. And we would say if you're looking at an f prime graph, it's where it decreases or has a negative slope. So that's what we would be looking at on our graph. Now whenever we see things that are concave, we know if they also over or under approximate. So if we were to find a point of inflection, or sorry, if we were given a tangent to something that was concave up, we would know that this point, if we were to draw a tangent line, see how it's below this curve. So this tangent would under approximate, where here if we were to draw a line tangent, it's above our curve, so we know that if it's concave down, it's going to over approximate. So concavity also helps with our under and over approximation when we're talking about derivatives or rates of change. Our first derivative test. This test determines relative mins and relative maxes. So if our derivative changes from positive to negative at some point c, then there is a relative max at x equals c. A relative max goes from positive to negative. So this is what makes a relative max on our original graph. So that means if we're looking at an f prime graph, if it changes from positive to negative, it's where it changes from above the x-axis to below the x-axis. If we were to take those values and draw it on a number line, for example, if we saw something like this and we were just mapping out what we saw on an f prime, we could see something like this where it's increasing, decreasing, increasing. We would say that this graph f has a relative maximum at A because f prime changes from positive to negative. So this would be our relative max. If it changes from negative to positive, that makes a minimum. So if we're looking at an f prime graph, that's where it's going from below the x-axis to above. And if we were to map out with a number line a graph where our f prime changes from negative to positive, say to negative, we would say, for example, that this has a relative minimum at x equals a because f prime changes from negative to positive. If our derivative does not change signs, say it's increasing and continues to increase, there's neither a min nor a max. So that could be something that stays above the x-axis when we're looking at our f prime graph. It is above the x-axis and stays above. This would be neither a min nor a max. And if we were, say, to map something like this out, it could stay above always, so there is no place where it is a min or a max. Second derivative test, you use the first derivative has to equal 0, and if the second derivative is greater than 0, it is a relative min. So if our first derivative has a slope of 0 here, and their f double prime is greater than 0, so that means our slope is positive, it would have a relative minimum. So normally you use this to solve for relative mins and maxes when given an equation. You could do it that way. If f prime of c is equal to 0 and our second derivative is less than 0, that would make it concave down, which would make it a relative maximum. All right, our extreme value theorem, the EVT. The EVT states if f is continuous on a closed interval AB, then there is an absolute max and an absolute min. So this is where you must check your critical points and your endpoints. Because remember, those endpoints, if you do your numbered line, this would make endpoint A a relative minimum because it is a left endpoint followed by f prime greater than 0. Point C here would also be a relative minimum because it is a right endpoint preceded by f prime less than 0. And we could do the same thing for maximums. We could say that A is a relative maximum because it is a left endpoint followed by f prime less than 0. Point C could also be a relative maximum because it is a right endpoint preceded by f prime greater than 0. So extreme value means you're looking for the absolute. Once you state all your relative, you have to always state all relative first. Then you're going to find the values for those relative minimums and choose the smallest of those values to find your absolute minimum. State all your relative maximums, find a value that is the greatest, and that would make your absolute maximum. All right, our fundamental theorem of calculus is if f is continuous on the closed interval AB, then this capital F of x, meaning the derivative or the integral antiderivative of f of x, is equal to the integral from a to x of f of t dt. There will be a derivative at every point where the derivative of capital F of x is equal to the derivative of the antiderivative when you go from a constant to a variable is going to just equal f of that variable. Now we have to also just remember in this case, if we were to do the derivative of a to x squared of f of t dt, we would have to make sure that we are substituting in derivative of the antiderivative. Our x squared is going to take place. It's going to become f of x squared, but we're going to have to use the chain rule and multiply by the derivative of the inside. So you have to remember the ones that are chain rule. Part B states if you have an integral of f of x from a to b, where a and b are both constants, that's the antiderivative of b minus the antiderivative of a. So that's your definite integral. You're taking the antiderivative of the upper minus the lower. So an example here, if g of x is equal to from the integral from 1 to x of f of t dt, then g prime of x means we're going to do the derivative of this antiderivative, which means that the x is going to take its place. And then remember that the integral finds the area under the curve. So if the area is below the x-axis, it's negative. If the area is above the x-axis, it would be positive. So an example would be if we go from 0 to a to b here, and this is, say, 10, and this is, we'll just say 2 pi. We would say the integral from 0 to a, and I'm going to call this f of x, of our function is equal to 10. Our integral from a to b of this function, since this is below, is going to be a negative 2 pi. And that means if we were to go from 0 to b, it would be 10 minus 2 pi. Now you have to always make sure that you include initial conditions when given, and we're going to experience that when we get to our free response next. So you have to remember to always include, if you're given specific values to start, when we go to apply this in our graph analysis. So our first free response here, we have the graph of the continuous function g, the derivative of the function f. So they're telling us right away that this is the derivative of f, is shown above. It says the function g is a piecewise linear function from -5 to 3. So piecewise linear means we could come up with the equations for all of these pieces. These are all linear functions. And then it is the function 2 times x minus 4 squared from 3 to 6. So this function is represented by this parabola or quadratic that we see here. So the first thing that we're given is that f of 1 is 3. So remember, this is that initial condition we were just talking about. So it says when we get to 1, our value is equal to 3. Even though when we look at this to get from 0 to 1, all we have is this triangle. And if we were to just do 1/2 base times height, our base is 1, our height is 2. So 1/2 base times height is just going to give us 1/2. Oh, I mean 1. 1/2 base times height. 1/2 of 1 times 2 is 1. But it's telling us it's not equal to 1. It's equal to 3. So we have to take this into account when we go to evaluate f of -5. So we're going to set this up in a different way. We know that f of 1 is 3. We're looking for f of -5. So in order to find that, if we know that f of 1 is 3, that means we're starting with 3. And that is the value f of 1. So we start with 3, and that is where we are then. We're at 1. We need to figure out negative 5. And this is, and I guess in here I could put f of x dx, which I guess is technically f prime or g when we write this. So I guess I could have g of x dx is the same as f prime f. So here I have the order is not correct, so I need to pull out a negative, so I can go from negative 1 to 5. And if that's my f prime, remember when you do the antiderivative of this, we're going to get the original. So that's what's going to give us our f of negative 5, because we're working backwards. When you integrate a derivative, you go back to the original. So if we're going from negative 5 to 1, negative 5 to 1 means we're going to take this shape here. We are also going to add here and up here. So we've got this rectangle, this triangle, this triangle. So I have this base is 1, 2, 3. My height is negative 3. So that's a negative 9. My triangle here, 1/2 base times height is going to be 1/2 of 1 times my height of negative 3. This area under this curve, well, this is just 0, so there's nothing to add here. And then my 1/2 base of 1 times my height of 2. So I'm left with negative 9. This is going to be minus 3 over 2, and then this is going to be plus 1. And then I can go ahead and combine these, so I'm left with a 3 minus, and then here I'm going to have negative 8 minus 3 over 2. And then this is going to become negative 16 over 2 minus 3 over 2 is 19 over 2. And this is a minus, a minus. And then when I can combine these, this is the same as 6 over 2 plus 19 over 2, or 25 over 2. So this is my f of negative 5. All right, part B says to evaluate from 1 to 6 of g of x dx. All right, so in this case, we're going from 1 to 6. So now we're just going from here to here. Since I knew f of 1 was 3, but I'm already starting here, I don't need that piece there. Okay, so but I do know that if I'm looking at this, I have this linear function and then I have this quadratic. So from 1 to 3, I have this area here, which is my base times height, and my base is 2 and my height is 2. So I can even just do, I'm going to just split this up for a minute. So I get 4 for this part. From 3 to 6, I have my function, which in this case, from 3 to 6, we were given from 3 to 6 that I'm going to use 2 times x minus 4 squared dx. So I have to know that I'm splitting it into 2 different ones. We've got our constant. We could have even done our constant variable because this is a linear function. If you notice, from 1 to 3 is just the equation of the line y equals 2. So if I wanted from 1 to 3, I could have 2 dx, because that's the equation of the function, which would become 2 times 3 minus 1, or 2 times 2, which is 4, which is exactly what we did here except I just did it using the rectangles like I did back in part A. But you could also substitute in the function 2 here and use your constant property. So in this case, we could look, if we have a function within a function. If u were equal to x minus 4, the derivative of u would just be dx. So we don't really need to use u sub because our du, dx are the same. So this is going to stay 2. I'm going to add 1. So that's going to be to the third over 3. And I'm going to evaluate that from 3 to 6. That 4 is not being evaluated from 3 to 6 because that is its own separate integral. That was its own area there. So I have 4 plus 2/3, and then I can have 6 minus 4, which is 2 cubed, or 8, and then 3 minus 4 is -1. -1 cubed is a -1, which becomes +1. And then we have 4 plus, this would be 9 times 2 is 18 over 3 is 6, and our final answer is 10. And that's our evaluating our integral from 1 to 6 of g of x. All right, for part C, for our -5 to 6, on what open intervals? So we're going to have parentheses around our intervals. We're looking for where our graph of f is both increasing and concave up. Well, since we know that g is equal to f prime, we're looking at our f prime graph. We're going to first identify our critical points, and our critical points are where our graph is equal to 0 or does not exist. And in this case, our critical points are happening at -1, 0. So if we were to make our number line here, -5, -1, and -1 to 0 is still staying 0. And then it touches again at 4. And then 6 is our end point. So by looking at our graph, we saw that it was above the x-axis. And I wonder if I can take a picture and kind of split this. Let me see. I don't know if I'll be able to do that and record at the same time. So, all right, if we were to look at our graph, it was below the x-axis from -5 all the way to 0. So it was below. Then between 0 and 4, it is above, and then it stays above. So when we go to look at our critical point in this case, and where it's increasing and concave up. So we know it's increasing from 0 to 4, and it continues to increase from 4 to 6. So we know it's increasing from 0 to 6. Now in order to be concave up, from 0 to 6 is where it's above the x-axis or increasing. And now to be concave up, our second derivative must also be positive or greater than 0. So we're looking for where the rate of change of this f prime or our slope is positive. And that happens here, and it also happens here. So we would say that the graph of f is both increasing and concave up and I'm going to say over -5 less than x less than 6. So it's increasing and concave up over -5 to 6 from, and that's happening, we said, from 0 to 1 and 4 to 6 because f prime of x is greater than 0 and f double prime of x is greater than 0. And you could say f prime of x is greater than 0 and f prime of x is increasing. This also just means f prime of x is increasing. All right, and then part D is asking us to find the x-coordinate of the points of inflection of the graph and give a reason for your answer. So we're looking for where our slope is 0 and changes signs. So our slope, we're looking for 0 slope or where our slope does not exist and is changing signs. So we have here our slope does not exist because we've got a corner, but if you see the slope is 0, the slope is increasing. So the slope is not changing signs. 0 slope doesn't have a sign. Here we have a positive slope, a 0 slope, positive slope. So it hasn't changed here. Then we go from a 0 to negative, but the signs aren't really changing there. Here we have a slope of 0 and it's going from a negative to a positive. So our point of inflection is occurring at x equals 4. Because f double prime of x equals 0 and changes from negative to positive. So our second derivative is 0 and changes signs. All right, then we get to our next free response question. And in this free response question, we are given a different graph. And in this graph, we have the graph of f prime. It says the function f is differentiable on the closed interval -6 to 5 and satisfies that f of -2 equals 7. The graph of f prime, the derivative of f, consists of a semicircle and 3 line segments as shown in the figure above. So the first part is asking us to find the values of f of -6 and f of 5. Well, once again, we have this given initial condition that tells us that at -2, we already have a function's value of 7. So whether that's represented in this picture or not is not what this question is saying. They're telling us this is true. So we know that no matter what, we start with 7, and that's our value at -2. So that's where we're starting. We want to find f of -6. So if we find the area under our f prime graph, we're going to get f. Now once again, this is not going from least to greatest, so we're going to have to change the sign so that it can go from least to greatest. And if we were to find from -6 to -2, that is our rectangle here is going to be 1/2. Our base is 1, 2, 3, 4, and our height is a +2. So this becomes half of 8 or 4, and 7 minus 4 is 3. So f of -6 is equal to 3. Now we're going to do the same thing, and now we're looking for f of 5. So we start with 7, but that's our value of f at -2 to 5 of f prime of x dx. So from -2 to 5 means we're going to do this semicircle and add this area of the triangle. So semicircle, we have 7 plus. Our semicircle is going to be pi r squared over 2, and our radius here is 2. And since it is below the x-axis, we have a negative. And then we're going to add our triangle 1/2, our base is 3, and our height is 2. So here we have 7. Here we get 4 over 2 is a negative 2 pi. And here we have half of 6 is 3. So f of 5 is equal to 10 minus 2 pi. So that using that initial condition is very important. Make sure that you include that. So part B, on what intervals is f increasing? Well, we can do our little number line to start. We're going from negative 6. We have a critical point here at negative 2, because that's where our f prime is equal to 0. We have a critical point at positive 2, and we have our end point at 5. And it's above the x-axis, so that's a positive, showing that it's increasing. Then we are below the x-axis to 2, and then we are back above the x-axis, so it's increasing again. So on what intervals is f increasing? So we know it's increasing from negative 6 to negative 2 and 2 to 5 because f prime of x is greater than 0. And oftentimes this is where on the AP test you will often see that they use brackets for both. So because it doesn't say on what open intervals, they will oftentimes have brackets around both. So it'd say negative 6 to negative 2 with a bracket and a bracket from 2 to 5. But we always just used our closed brackets for our endpoints to include. All right. So they only do that for increasing and decreasing functions, I've noticed. Part C, find the absolute minimum value of f on the closed interval and justify your answer. Well, before we can find the absolute minimum, we have to state all of our relative minimums. So we're going to use this number line here. We see that since it's saying on the closed interval, we have to look at our endpoints. So we start with negative 6. This is a low point. See how it's followed by increasing? So x equals negative 6 is a relative minimum. And we would say because it is a left endpoint followed by f prime of x greater than 0, then we would look and see, since we're increasing then decreasing, now we're increasing again, we also have a relative min. So x equals 2 is a relative minimum because f prime of x changes from negative to positive. And now they're not asking, though, for us to just list our relatives. They want to know, find the absolute minimum value. So we need to find what these values are, the y values of this function when x is negative 6 and x is 2, and we're looking for the minimum of those. So we need to start by stating what f of negative 6 is. Well, we found f of negative 6 here in part A. F of negative 6 is 3. And now we need to find f of 2. We didn't find f of 2. So that means in order to find f of 2, we're going to need to go back and find f of 2. So that means we're going to have to use our initial condition again. So we're going to say 7 plus. Now 7 was our value when f was negative 2, or when x was negative 2. We're looking for 2. So that means we're going to look from negative 2 to 2 is our semicircle. So it's that 1/2 pi r squared Well, we found that here, that was a negative 2 pi. So f of 2 is 7, and I'm going to make this a minus 2 pi. So if we were to compare 3 and 7 minus 2 pi, well, we know that pi is approximately 3.14. So this would be 7 minus 6.28 is smaller than 3. We would state the absolute minimum value on negative 6 to 5, because they gave us that specific interval, is 7 minus 2 pi. Remember, they asked for the minimum value. They did not ask for the x-coordinate. So the absolute minimum value is 7 minus 2 pi because f of 2 is less than f of negative 6. And our last part is asking us to find f double prime of negative 5 and f double prime of 3, find the value or explain why it does not exist. So we're going to start f double prime of negative 5. This is the f prime graph. So if we're looking for f double prime, we're looking for the rate of change or the slope of this graph at negative 5. Since this is a linear function, we can just count our rise over run. We're going down 2 and over 1, 2, 3, 4. This line all has the same slope, so that's going to be a negative 1/2. To find f double prime of 3, we need to find the slope at 3, but if you notice, this is a corner, so the slope does not exist, but you have to be able to show or explain why it does not exist. So mathematically, the best way to show that this does not exist is to do limits. So if we did the limit as we were approaching 3 of f prime of x from the left. So if you notice, we're approaching 3 from the left. We have a slope of up 1 over 2. So we'd have a slope of 2. If we were to find the limit of f prime of x as we approach 3 from the right, if we were coming towards 3 from the right, we have a slope of down 2 over 2 is a slope of negative 1. So if our limit from the left and our limit from the right are not the same, that means the limit does not exist. So we would say that f double prime of 3, and we could actually, let's state that first. The limit of f prime of x as x approaches 3 from the left does not equal the limit of f prime of x as x approaches 3 from the right. Therefore, f prime of x is not differentiable at x equals 3. So if it's non-differentiable, and you can even say up here, f double prime of 3 does not exist because there's a corner, this is mathematically what makes the corner. All right, so those are the derivative graph analysis free response questions. And then lastly were the multiple choice questions. And these questions you actually did back when we did our graph analysis review for our test. So I'm going to just give the answers to these, and then if you want to work through any of these, we can absolutely work through some of them. But the first one, inflection points, remember, it has to equal 0. So we have at x equals 0, we have at x equals negative 1, and at x equals 2. So when you go to do your number line test at negative 1, 0, and 2, the signs must also change for the second derivative. So if we were to pick a number, say negative 2, and substitute it in, we would have a negative, a negative 2 here would give us a negative, and a negative 2 here would give us a negative that gets squared or is a positive. So a negative times a positive is a positive. If we were to pick a number like negative 1/2, we would have a negative times a negative times, oops, this would be a positive. A negative times a positive times a positive makes a negative. So the signs are changing, which means this so far is, yes, a point of inflection. If we were to pick a number between 0 and 2, like 1, we would have a positive times a positive times a positive. So the signs are changing here. Here's another point of inflection. And then if we were to pick a number greater than 2, like 3, we would have a positive times a positive times a positive. The signs do not change, so negative 1 and 0 are the only ones that can be points of inflection. And we might as well just go through these just to see. So this next one, the graphs of the derivative functions f, g, and h are shown above. Which of these functions have a relative maximum? So remember, relative maximum has to change from positive to negative, which means it needs to go from above the x-axis to below. So here we are above, we're going below, so yes, we have a maximum, a relative maximum here. Here we are above, but we never go below. Here we are above, but we never go below. So the only one that has it is f. Find our values for where f of x equals e to the x is increasing. Well, increasing and decreasing, you always have to find the derivative first. Our derivative of e to the x is e to the x. E to the x is always increasing. We have an horizontal asymptote at 0. All of our values are above the x-axis, so it's increasing always. Our derivative g prime of a function g is continuous and has exactly 2 zeros. Selected values of g prime are given in the table above. If the domain of g is the set of all real numbers, then g is decreasing on which intervals? Well, this is g prime. We've got to find our critical points. So where g prime of x equals 0, and it's decreasing between the two. So this is one of those cases, increasing and decreasing. They always like to include those critical points on the AP test when they're talking about increasing and decreasing. So this would be from -2 to 2. Number 5, how many critical points does this function have? Well, don't get fooled. This is just f of x. We have to find f prime of x. So critical points is where f prime of x is equal to 0. And in this case, we're going to have to do product and chain rule. So we have to do our first, x plus 2 to the 5th, times the derivative of the second. Well, the derivative of this means the 4 comes in front, x minus 3 to the 3rd times the derivative of the inside is just a 1, plus the second, x minus 3 to the 4th times the derivative of the first, the 5 goes out front, x plus 2, we subtract 1, derivative of the inside is just 1. Now these have common factors that we can take out, so we want to take out what they have in common. They both have x plus 2, and in common they have 4 of them. They both have x minus 3, and in common they have 3 of them. And then left over here, we have a 4, and we have an x plus 2, which makes 4x plus 8. Here we have a 5, and we have an x minus 3, which makes 5x minus 15. And then when we combine like terms, we have an x plus 2 to the 4th, x minus 3 cubed, and this becomes a 9x minus 7. That is our derivative, and when we set these equal to 0, we'll get a negative 2 as a critical point. We'll get a positive 3, and we'll get a 7 over 9, so there are 3 critical points. Number 6, the graph of a twice differentiable function f, so this is the graph of f, not f prime, is shown above. Which of the following is true? Well, looking at this graph, we know that f of 1 is 0. If we were to look at the rate of change, or the slope at 1, it's increasing, so it's greater than 0. If we talk about the second derivative, we're talking about concavity. This is concave down, so it's less than 0. So if we were going to go from least to greatest, our smallest one is our second derivative, then our f of 1, then our f prime of 1. And the last one is a calculator question. The first derivative is given. How many critical values? So we're looking for where this is equal to 0 on the open interval 0 to 10. So we are going to go to our y equals, and we are going to type our equation in. We have a cosine squared, so we're going to have cosine of x squared I'm going to go ahead and change that and close my parentheses and then squared. So cosine of, let's try this one more time. So we've got cosine of x squared. That's much better because it's the entire cosine squared x, so we want cosine x times cosine x all over x minus, and then we have 1 over 5. You want to change your window. It says on the open interval 0 to 10. And since we're looking for where y equals 0, we can even change our y values -2 to 2 or -1 to 1 because we only care about where y is going to be equal to 0. And then we can graph this. So we're looking for where it is equal to 0. And I'm going to even make my y's smaller, so we can clearly see from -1 to 1. So I see it crossing the x-axis or equal to 0 1, 2, 3 times. Here it doesn't quite equal 0, so I see 3 different places. So that would be the answer. All right, so those are the practice problems on graph analysis, and let me know if you have any questions. Have a great night.